Hey there, how's it going everybody? In this video, we're going to be learning all about AsyncIO in Python. AsyncIO is Python's built-in library for writing concurrent code, and it can seem a bit intimidating at first with all the different terminology and moving parts, but by the end of this tutorial, I'm hoping that you'll have a solid understanding of how it works and when to use it. Now in this video, I'm going to be covering a lot. We're going to be learning how AsyncIO actually works under the hood. We'll see visually what's happening with some animations that I've put together. We'll see how to update an existing code base to use AsyncIO. We're going to be able to determine when and where to use AsyncIO with some simple profiling. And we'll discuss when to choose async versus threads versus multiprocessing. And the code and the animations that I'm going to use in this video are going to be available on my GitHub and website after this is out. So if you all want to follow along with those yourselves, then I'll leave links to those in the description section below. Now, I'm going to get to some code as soon as I can, but there's a few basics that we have to get out of the way first. So AsyncIO is a Python library for writing concurrent code using the async await syntax. And I want to mention that we're using the latest version of Python in this video, and I'll be teaching the current way to do things. AsyncIO has evolved quite a bit over the years. There have been different ways of running the event loop, scheduling and running tasks, and all kinds of different changes. But we're going to focus on the modern ways that you should be using today. Now, before we dive too deep, let's talk about what concurrency actually is. So with synchronous code execution, which is what we normally write, one thing happens after another. So it's kind of like going to a Subway restaurant where you put in your order and they make your entire sandwich from start to finish before moving on to the next customer. But with concurrent code, it's more like going to a McDonald's where someone just takes your order and then moves on to the next customer while your food is being made in the background. And that difference, when applied to code, can be really confusing at first for a lot of people. So here's something that I think is important to understand pretty early on. So asynchronous doesn't automatically mean faster. It just means that we can do other useful work instead of sitting idly by while waiting for things like network requests and database queries and stuff like that. That's why AsyncIO excels at what's called IO-bound tasks, which are anytime your program is waiting for something external. Now, AsyncIO is single-threaded and runs on a single process. It uses what's called cooperative multitasking, where tasks voluntarily give up control. For CPU-bound tasks that need heavy computation, you'd want to use processes instead, and we'll see how to tell the difference between IO-bound and CPU-bound here in a bit. But before I lose your attention with too much theory early on, let's go ahead and jump into some code, and we'll learn the basic terminology that we need to know as we go. So let me walk through this code and explain the terminology as we go. Now, the terminology is what really trips a lot of people up when they first start learning AsyncIO because there's quite a bit to remember. Now, right now, we have some asynchronous code here that we'll walk through and explain. But for now, you can see that we have a simple synchronous function right here at the top, and that just sleeps for a bit, and then it returns a string. We're running this synchronous function inside of our main function here. Our main function is asynchronous, and you can see that it has this async keyword. Since it's an asynchronous function, we can't just call it directly. In order to run our main function, we have to start what is called an event loop. And we're doing this down here at the bottom with AsyncIO.run and passing in that main async function there. So the event loop is basically the engine that runs and manages asynchronous functions. Think of it a bit as a scheduler. It keeps track of all our tasks, and when a task is suspended because it's waiting for something else, control returns to the event loop, which then finds another task to either start or resume. So we have to be running an event loop for any of our asynchronous code to work. That's what this AsyncIO.run function is responsible for. It's getting the event loop, running tasks until they're marked as complete, and then closing down the event loop whenever it's done. So let me go ahead and run the code that we have right now. And we can see that we're just printing out that this is a synchronous function, and then we get that result. So we came in here, ran this event loop. This is an asynchronous main function, and we're just calling this synchronous code here within our async function for now. But we don't want to just run synchronous functions inside of our event loop. We want to use concurrency. To use concurrency, we're going to be seeing this await keyword a lot. So let me uncomment the futures code here so that we can talk about awaitables. So let me uncomment this here. So you can see here that we're using this await keyword. So awaitables are objects that implement a special await method under the hood. You're going to see await everywhere in asynchronous code. An object has to be awaitable for us to use that keyword on it. Now, why can't we await a synchronous function like this sync function here or something like time.sleep? Well, synchronous libraries don't have a mechanism to work with the event loop. They don't know how to yield control over and resume later. So basically, synchronous code like time.sleep or our synchronous function here, they don't have that underlying special await function that they need in order to pause their execution and start back later. These things need to be coded in to be compatible with AsyncIO, and that's why we can't await time.sleep, and we need to use something like AsyncIO.sleep instead. And to use this await keyword, we also have to be within a function that has this async keyword. So if I remove async from our function there, now you can see that I'm getting a warning here. And if I hover over this, it's not letting me hover right now, but we can see that my rough warning here is telling me that await should be used within an async function. So we have to be within an async function in order to use these await keywords. Okay, so what does await do? So when you await something, you're basically telling the event loop to pause the execution of the current function and yield control back to the event loop, which can then run another task. And it'll stay suspended until this awaitable completes. So in Python's AsyncIO, there are three main types of awaitable objects. First, there are coroutines, which are created when you call an async function. Second, there are tasks, and tasks are wrappers around coroutines that are scheduled on the event loop. And the third, there are futures, and futures are low-level objects representing eventual results. Now, if you're coming from somewhere like the JavaScript world, futures are a lot like promises in JavaScript. They're a promise of a result that will be available later. But unlike JavaScript, in Python, we almost never work with futures directly. We write coroutines, and when we schedule them as tasks, AsyncIO uses futures under the hood to track those results, but we won't be seeing them much in this video. You're really only going to use futures directly if you were writing low-level AsyncIO code, like if you were building an AsyncIO compatible framework. But just to show you what they look like, let me run this example with this futures example here really quick, and just so we can see what's happening. So a future's job is to hold a certain state and result. The state can be pending, meaning the future doesn't have any result or exception yet. It can be canceled if it was canceled using future.cancel, or it can be finished. And it can be finished by a result being set by future.setResult, or it can be an exception with future.setException. So you can see here after we created this future and printed that out, it says that future was pending after we created it. And then we set the result right here to future result test and got that result by awaiting it. And then we printed that out. But like I said, this is lower level stuff, and we won't be using it directly in this video. We're going to be working mostly with coroutines and tasks. So I'm going to delete this future example here, and then we're going to look at coroutines and tasks. So let me uncomment the coroutine example here. And coroutines are functions defined with the async def keywords here. So main is a coroutine here. We have async def. If I go up here, we have this async function, and I have a comment here that says also known as a coroutine function. So we have this async def, async function. And within here, it's a lot like our synchronous function, but instead of using time.sleep, we are using AsyncIO.sleep, and we are awaiting that as well. So that's what this coroutine object is right here. So coroutines are basically functions whose execution we can pause. And there's actually two terms here that we need to understand. There's the coroutine function, which is what we define with the async def keywords. And then there's the coroutine object, which is the awaitable that gets returned when you call that function. So this is the coroutine function here. And after we call that function, this is the coroutine object here. So coroutines are a bit like generators in the sense that they can suspend execution and resume later, but they're designed to work with an event loop. They have extra features that AsyncIO needs to schedule them, await I/O, and coordinate multiple tasks. So let me go ahead and run this here so that we can see what's happening. Now, again, if you're a bit confused right now, I think all of this will make a lot more sense once we look at the animations that I've put together. But right now, we're just focusing on learning these terms so that we can understand a bit better what we're looking at once we get to those animations. So you can see here, when we executed this coroutine function, it doesn't run all of that function. It didn't come in here and print out that this was a synchronous function before we got to this line here. It just created this coroutine object, and then we printed out that coroutine object, which is right here. So when we ran that coroutine function, we got this coroutine object, and to actually run this coroutine and get the result, we have to await it. When I await that coroutine object, we can see that that's whenever it runs the print statement from our asynchronous function, and then we got that result and printed that out, and that result was just async result test. Now, when we await a coroutine object directly like this, it's both scheduled on the event loop and run to completion at the same time. Okay, so now let's look at tasks. So I'm going to comment out this coroutine section here, and now let's look at tasks here. Now, tasks are wrapped coroutines that can be executed independently. Tasks are how we actually run coroutines concurrently. When you wrap a coroutine in a task using AsyncIO.createTask like we've done here, it's handed over to the event loop and scheduled to run whenever it gets a chance. The task will keep track of whether the coroutine finished successfully, raised an error, or got canceled, just like a future would. And in fact, tasks are futures under the hood, but with extra logic to actually run the coroutine and do the work that we want to do. That's why we work with tasks instead of futures in most of our code. But unlike coroutine objects, tasks can be scheduled on the event loop and just sit there without being run until the loop gets control. And this is the key to AsyncIO. You can queue up multiple tasks at once, and then the event loop will be able to run them whenever it's ready, letting them take turns while waiting on I/O. So let me go ahead and run this so we can see this basic example here. So you can see that when we printed out the task that we created here, it shows that the task is pending. It shows us the name of the task here and the coroutine that it is wrapping. And when we await that task, it runs that coroutine and we get those print statements and that returned result. Okay, so that does it for the terminology. Now let's see this in action with some specific examples and some animations. I don't know about you all, but I'm a very visual learner. So seeing this stuff in action helps me a lot more than just looking at the code. So first, I'll show the Python code, and then we'll see what's happening under the hood with an animation. So here is the Python code here. Now, in this first example, we're not going to be using AsyncIO at all. This is just normal synchronous code with no event loop or anything like that. So we should know exactly how this works. So if we go down and look at the code here, we are setting the results equal to this main function here. And don't worry, I have some extra timing functionality here just so we can see how long this takes. But then we're running that main function. The main function comes in here, and we are running this fetch data function with a value of 1. Fetch data then comes in here, prints out that we're doing something with 1, then it sleeps for that 1 second that we passed in, then it prints that we're done with 1, and then returns the result of 1, okay? And then after that returns, that return value gets set to that variable there. Then we print that fetch 1's fully complete, and then we come here and do result 2 is equal to fetch data 2. That comes up here and says do something with 2, time.sleep for 2, done with 2, then returns result of 2 to this result 2 here. We print out that fetch 2 is fully complete, and then we return both of those results. So fully synchronous code, we should know how this works. Let me go ahead and run it. And I added some timing code here that'll show us how long this took. So we can see it ran through that code synchronously and it finished in 3 seconds. And that makes sense because we're doing fetch data for 1 second and then we're doing fetch data for 2 seconds. So 3 seconds total. So now let me show this as an animation in the browser so that we can get an idea of what these animations are going to look like. And I've taken the timing code out of these animation examples so that we can just pay more attention to the actual code. Okay, so let me go to example 1 here. Sorry about that. Now, hopefully this text is large enough for you to see. I made this as large as I could while everything can still fit on the screen here. Now, if you're walking through these examples, these animations with me by using my website or have downloaded these yourself, then I've set this up so that the right arrow key progresses to the next steps. And unfortunately, I didn't add any functionality to go backwards. So if you want the animation to run again, then you'll have to reload the page. Okay. So like I said, all of this is synchronous code here. So we're just going to walk through this. It's going to see those functions there. Then we're going to run result equals main there. It's going to go into the main function. And none of this is going to kick off anything on the event loop. We are going to run fetch data with the parameter of 1. That's going to come in and run some print statements. We're going to do a time.sleep. Now, time.sleep is going to kick off some background IO here and sleep for 1 second. And it's going to stay on this line for that entire second until that completes. Once that completes, then we can move forward and do our other print statements here, return that, and then we're going to walk through, do result 2 is equal to fetch data 2. Same thing, we're printing out some text there. We're going to run this background IO. It's going to sleep for 2 seconds now, and that's going to stay there until that completes. Once that is done, then we can come in and print out our other statements, and then we return our result 1 and 2, and then we come down here and print the results that we got from main, which was just a list of those 2 results. Okay, so that's synchronous code. That should be what we expect. But since it was synchronous, we were waiting around during those sleeps when we could have been allowing other code to run. So now we might want to improve this performance and switch over to using AsyncIO. So let's move on to example 2 here and see an example of how someone might go about doing this. Now in this example, we're going to see what a first attempt at converting our code to asynchronous might look like, but there's going to be a common mistake here. So you can see that we've converted our functions into coroutines. So we have an async def fetch data here. Our main is async def coroutine here. And then we are running this in an event loop here with AsyncIO.run. So this is what someone's first attempt might look like to go asynchronous here. So we are setting our tasks here directly to our coroutine objects here, fetch data 1 and fetch data 2, almost like we're just calling a function. This is very similar if we go back to example 1, how we were setting the result equal to fetch data 1 and fetch data 2. That's what we're doing here with these tasks. And then we're trying to get the result here by awaiting those coroutines directly. And then after we await 1, we're printing out that task 1 is fully complete. After we await 2, we're printing out that task 2 is fully complete. Now we could have awaited these directly. I could have said that result 1 is equal to await fetch data 1 like that. But I broke them up here into being able to see the coroutine object first and then await that separately. Okay, so let's run this and see if this works. So we run this code and we can see that it still takes 3 seconds. So we're not getting any concurrency benefit here at all. So why is that? Well, some people have a misconception that when you run a coroutine function like we did here, that it creates a task and schedules it, but it doesn't. It just creates the coroutine object. So when we await that coroutine object, we're scheduling that and running it to completion at the same time. We get no concurrency here and no benefit to using AsyncIO. So let me show you what this looks like in an animation that I put together, and I think this will make more sense. So here we have that same code that we had before. So we're going to run through this. Now, once we get to results equals asyncIO.run main, that is going to create our event loop. So now in our event loop, right now we have one coroutine. We have this main coroutine that is going to run. So now the code, whenever I step forward here, it's going to run from this coroutine here. So as I go through this, now we're saying task is equal to fetch data 1. That's going to create a coroutine object. Task 2, that's going to be another coroutine object. And now when we do result 1 equal to await task 1, that is going to schedule that on our event loop and run it to completion at the same time. So if I step forward here, then our main coroutine is suspended. So await is what suspended our main coroutine. And now our event loop is looking for tasks that are ready. Now we just scheduled that fetch data 1 task whenever we ran this coroutine directly. So our event loop is going to see that and say, okay, I have a ready task here. So let me go in here and run this until I hit an await. So now it's going to come in here. It's going to print that we're doing something with 1. And then we are going to await that sleep. And once we hit that, it's going to suspend our current task, and it's going to be suspended until asyncIO.sleep is complete. So that's going to kick off our background IO here with our timer, and then that's going to suspend. And now that's going to stay suspended until our timer is complete. Once that timer is complete, then this is going to wake up this task and say, hey, what you were awaiting here is complete. So now you're going to be ready to run again. So now that completed, now we're ready to run again. Our event loop is going to go through, see that we have a ready task here, and then it's going to go back in and it's going to continue running from where it left off. So then we're going to go through here, print out these other statements, and finally we're going to return here. And once we return, now this task is complete. This fetch data 1 task is complete, and that is going to wake up our main coroutine here, because now this task 1 that we were waiting for is now complete. So now main is ready to run again. Our event loop is going to see that. It's going to come in here and run it, and now print out task 1 fully complete. And now we're going to do the same thing with await task 2. It's going to suspend our main coroutine. It's going to schedule our task 2 here onto our event loop and also run it to completion. So we're coming in here and we are printing these out. This await asyncIO.sleep here is going to suspend this task until this asyncIO.sleep is done. So it kicks off that timer. It suspends our task. That timer eventually is going to complete. Once that's complete, then our task can wake up here, and now it's ready to run. The event loop is going to see that, run it where it left off at this await statement, and then we're going to walk through our other print statements here, hit our return statement, and that's going to complete that task. And now, since task 2 is complete, and that's what we were awaiting there, now our main coroutine is ready to run again. So now our event loop is going to see that we have a ready task here, come in and finish printing these out, and then finally it will return that main coroutine, and close all of that down. And then back here in our main Python code, we get those results and we can print those out. So I hope that that made sense. Let me reload this really quick. I won't go through the entire animation again, but the one thing that I really want you to catch on to here is that whenever we created these coroutines here, they are not scheduling any tasks on our event loop. They are just returning a coroutine object. And then here, when we await those coroutine objects directly, we are both scheduling them and running them to completion at the same time. So that is why we are not getting concurrency. We only have one task down here that is ever running at a time. So basically, we have the same performance that we had when we ran our synchronous code. So let me go back to our code here. And now let's look at example 3. And this is going to be a look at one of the correct ways to run asynchronous code. Now, the only thing that we've changed here from the previous example is that now we are creating tasks from these coroutines using AsyncIO.createTask instead of just calling those coroutines directly. Now, when we create a task, it schedules a coroutine to run on the event loop. This is the part that we were missing from the previous example. So now if I run this, then we can see that in our output that do something with 1 and do something with 2 ran one after another without the first task finishing and before task 1 was able to print out that it was done or task 1 was fully complete. It immediately came in here and said, okay, I'm going to do something with 1, I'm going to do something with 2. And then since our number 1 task only slept for 1 second, it completed first. And then our second task completed after that, since it's sleeping for 2 seconds. And we can see here that the total time of our script here took 2 seconds in total. And that is because it ran both those at the same time. And that total time is simply how long the longest running task was, which was 2 seconds. So we did get concurrency here. So let's see this in an animation so that we can see exactly what that looks like. Okay, so now here we can see that I have the code that creates the task here. So let me walk through this. And again, we're going to get to this line here where we are running our event loop and we're going to run this main coroutine. So that main coroutine is now running on our event loop. And then when we get to this point here where we create this task with fetch data 1, that is going to schedule that task on the event loop. So now we can see that that task is now scheduled and ready on the event loop. And now in our main coroutine here, we're still going forward. And now with task 2 with AsyncIO.createTask, that is also going to schedule that fetch data 2 on our event loop. So now we can see that that gets scheduled as well, and both of those are ready. And now when we get to this line here, result 1 equals await task 1, this await is going to yield control over to the event loop, and it's going to suspend our main coroutine here until this task 1 is complete. So if we go forward with that, our main coroutine suspends here, and now our event loop is going to look for any ready tasks. It's going to see that we have fetch data 1 ready, so it's going to come in, it's going to run this, and then it's going to hit an await statement here. And now it's going to suspend this task until AsyncIO.sleep is done. So it's going to kick off that AsyncIO.sleep here in the background, and now it's going to suspend that task. Now, this is where we get concurrency. Since we had both of these scheduled, now our event loop is going to keep looking for tasks that are ready. It's going to see that we have this fetch data 2 here, and now it's going to come in and run this. So we're going to do our print statements here. We're going to hit our await, which is going to suspend our fetch data 2 coroutine, and it's going to be suspended until AsyncIO.sleep is done, and that's going to be the one for 2 seconds. So it's going to kick that off, then it's going to suspend, and now you can see that this is the concurrency here. We have both of these timers running here in the background. So these are all going to stay suspended until something gets finished. So our first timer completes. It's going to wake up our first task here. And now that that first task is ready, our event loop is going to find a ready task. And then it's going to pick up where it left off and just print that we are done with one and then return that value. And now, once that is complete, remember that our main coroutine is awaiting that task one. So as soon as this task one is complete, then our main coroutine is now ready to run again. So it's going to come in here and print out that task one is fully complete. We're going to await our task two. Now task two is already suspended, so there's nothing really to do here other than to wait for this timer to finish here. Once that timer is complete, it's going to wake up this fetch data 2 task here. Now our event loop is going to see that that's ready, come in here where it left off, and print out that we're done with 2, return the results. And now that this is complete, our task 2, it's going to tell our main coroutine that it's ready to run. Our event loop is going to see that and run where that left off, print that task 2 is fully complete, and return a list of those results. And then that event loop is going to close down. We have those results there. We can print those out, and we have everything there. So I hope that that example makes sense, and now it makes sense why this code worked here by scheduling these tasks ahead of time instead of whenever we awaited these coroutines directly. Because when we awaited these coroutines directly, it didn't get scheduled until we hit this await statement. So we only had one task scheduled and run fully to completion here. In our second example, we had both of these tasks scheduled, and then when we awaited, it was able to run our task 1 until it hit an await, and then once we hit that await, then it was able to go through and see that we had another task that was ready and scheduled, and it could run that as well. Okay, so I hope that that makes sense. The more examples that we see, I think the more clear that this is going to be. Now, in our fourth example here, now I want to show you an example of something to show you something important about awaiting tasks and how things are actually run on the event loop here. So I haven't changed much with this code here. It's basically all the same, but all I did here from example 3, in example 3, I'm awaiting task 1 first and then printing out that task 1 is fully complete. In example 4, I am setting result 2 and I'm awaiting task 2 first and printing out that task 2 is fully complete. And then I am awaiting task 1 and saying that task 1 is fully complete. Now, what do you think is going to happen here when I run this? So some people might think that we're going to run task 2 first and then task 1, or maybe run them both at the same time, but that task 2 will complete first. But let's see. Let's go ahead and run this and see what happens. So when I run this, then our results might be a little confusing to some people. So we still finished in 2 seconds, so it's still running concurrently. But if you look at the output, task 1 still runs first. There's no change there. The only difference is that it didn't move to our task 2 fully completed print statement here until task 2 was completely done. So that's what I want you to take away from this specific example, is that when we await something, we're not guaranteeing that we run that particular part right at that moment. The event loop is going to run whatever is ready. What we are guaranteeing is that we're going to be done with what we awaited before moving on. And actually, it doesn't even need to be one of these tasks that we await. So for example, I could use AsyncIO.sleep here instead, and that would also yield control to our event loop, and those tasks would still run in the same order, and it just wouldn't move on until our AsyncIO.sleep is done. So let me do that and just show you what I mean. So I'm going to await AsyncIO.sleep. Since our longest sleep is 2 seconds, then I'll just sleep here for 2.5 seconds. So if I run this, then it's going to be the same output pretty much, except now we don't have a second result because await AsyncIO.sleep just returns none. So our result 2 there is none. And it finished in 2.5 seconds since that's now the longest sleep that we have. But we can see that the order of execution basically remains the same. It still did something with 1 first, then 2, got done with 1, got done with 2, and then once this awaited AsyncIO.sleep was finished here, that is when we moved on to printing out that task 2 is fully complete there. So that is what I wanted to show you with that example. Let me also show you this here in an animation just to really hammer that point home. So I'll start stepping through the first part of this pretty quickly now. So we're going to get down to where we run our event loop with that main coroutine. And then that is going to create our first task there with task 1. It's going to schedule that. Our task 2 with create task is going to get scheduled as well. And this time we are awaiting task 2 first. Now when we hit await, what it's going to do is it's going to suspend this coroutine until task 2 is done. So we're suspending and we're yielding control back over to the event loop. The event loop is going to go and see what tasks are ready. Now this uses a FIFO queue in the background, which is first in, first out. That's not super important, but what is important is just to know that what you're awaiting isn't always going to be the first thing that gets run. It's just going to be whatever the event loop has ready. So right now it is this fetch data task 1 here, and that is going to run until it hits its await statement and suspends itself and kicks off that background sleep. And now we have another task ready here. The event loop's going to see that, going to come in until that hits its await statement. It's going to kick off that background sleep, and it's going to suspend itself until one of these timers is done. Then this timer is done here. It's going to wake up our first task here. And now this is where something a little different happens that was different than our previous example. So it's going to see that this is ready. It's going to come in and pick up where it left off here. We're going to print that we're done with 1 and return that result. And that is going to complete. Now, before we were awaiting task 1 here. So before, once this task 1 was done, then our main coroutine was going to say, okay, I'm ready to run again. But that's not what we awaited. We awaited task 2. So what this is going to do is it's just going to save that result in memory for now. And now we still just have 2 suspended coroutines here. So these are going to stay suspended until this timer completes here. That completes, it's going to wake up this second task. And then our event loop is going to see that that is ready. It's going to come in and do its print statements that it's done with 2. It's going to return that result. And now our main coroutine is going to get woken up whenever this task 2 is done here. So now it is saying that it's ready, and now we move forward with our print statements. So we're going to print that task 2 was fully completed. When we do this await task 1 here, that's already been completed, so there's nothing left to do there. All it's going to do is pull that result from memory that it has saved, so it's just going to set that variable equal to what that return value was. We're going to print out that task 1 is fully completed and then return a list of those results, close down the event loop, and move through and print out all of those. Okay, so I hope that this is making more and more sense as we're seeing more and more examples here. Okay, so moving on to our next example. Our next example here is going to be really important. So let me pull this one up here. Now, in this example, we're going to see what happens if we block the event loop with synchronous blocking code. So this is pretty much the same as the examples that we've been looking at, where we are creating tasks, scheduling those on the event loop, and then awaiting those tasks. But in our fetch data coroutine here, instead of using AsyncIO.sleep, I'm using time.sleep here. Now, time itself isn't awaitable, so I can't await that here. If I put in await, then that's just going to throw an error. But what we can do is we can run this inside of an asynchronous function like fetch data, and we can schedule that on our event loop, and we can await that coroutine. But this is bad practice here, and we're going to see exactly why. Because like I was saying before, time.sleep isn't awaitable, and it wasn't coded to know how to suspend itself and yield control over to the event loop. But what happens if we put that blocking call there and then schedule and run that coroutine? Well, let's go ahead and see. So I'm going to go ahead and run this, and we can see that it did something with 1, did something with 2, task 1 fully complete, task 2 fully complete, and we finished in 3 seconds here. So since we finished in 3 seconds, we know that those didn't run concurrently. We can also see that it didn't start both of these at the same time either. We came in and did something with 1, and it wasn't until we were done with 1 that it moved on to doing something with 2. And that's because time.sleep blocks the event loop. Now, that might not be obvious, and some people might think that just because we had that synchronous code being run inside of a task, that we assume that maybe somehow it would have worked. But let me show you what's actually going on here and why this blocks. So I'm going to pull up our 5th example here, and let's go ahead and run through this to see what happens. So I'm just going to go down to the part where we start our event loop and run that main coroutine there. And now within the event loop, we are scheduling our task here and creating those. And now we're getting to the point here where we are awaiting task 1. So that's going to suspend our main coroutine, and it's not going to pick back up on our main coroutine until task 1 is complete. So I'll go ahead and move forward here. That's going to suspend. Our event loop is going to find a task that is ready to run. It's going to come in here into fetch data 1, and it's going to run down through this. We're going to print that we're doing something with 1, and now we're going to get to this time.sleep. Now here, it's going to kick off that background IO here. But what's going on is that we never awaited here. So this task never got suspended. So it's just going to sit here until this blocking code is done, until this background IO is done. So what we have here is a blocked event loop. So eventually that sleep is going to complete. There's nothing to wake up here because we're still just running synchronous code. So now that that's complete, we can run forward with our task here, say that we're done with 1, return that result. Our main coroutine is going to wake up here. Now, again, like I was saying before, even though our main coroutine is now ready because that task 1 was complete, that doesn't necessarily mean that that is the next thing that the event loop is going to run. The event loop uses that FIFO first in, first out queue in the background. And since task 2 has been ready for a while and was ready before main became ready again, then it's going to actually find this task 2 first. And this is where my animation is lacking a bit because it doesn't show that FIFO order of the ready queue, but that's what's going on there. So it's going to see that our task 2 is ready here. We're going to come in and run this. We're going to print out a couple of things. We're going to get to this time.sleep. That time.sleep is going to kick off our background IO, but it does not know how to suspend itself. So it's just going to hang here until this sleep is complete. Once that sleep is complete, then this can continue on and print that we're done with that. It's going to return that result. Now our main coroutine here has been ready for a while. Our event loop's going to see that. It's going to come in and print out the rest of these print statements, close down the event loop, and then we will print out our results there. Now let me restart this animation really quick, and I'm just going to go back to a certain part of this animation. It's where we completed our first task here, and now both of these tasks are ready. And like I said, this is a FIFO queue where it's going to find this task number 2 first and run this. Now you might be thinking that I should be emphasizing the order in which these run a little bit more and kind of explain that a little bit more. But to be completely honest, you don't really want to get bogged down in what exactly is running on the event loop at any one time, or what's going to be next, or anything like that. Because AsyncIO, it's really meant we're going to be running, tens, possibly even hundreds of things concurrently, and the event loop is going to handle everything that is ready. When we run real asynchronous code, it's not going to be cut and dry examples like we have here, where we know exactly when most tasks will be finished and when others will be ready. So we don't have control over that, and we shouldn't want to have control over that. The event loop is just going to do its job. What we do have control over is not moving forward until something is done. So if I didn't want this to move forward until task 2 was done, then I would put an await task 2 there. But in terms of whether this goes back and runs the main coroutine or fetch data first, that shouldn't really matter that much to us. Let the event loop run whatever tasks are ready. And if we really want to enforce anything, it'll be that we're going to enforce exactly when something is done, not, exactly whenever it gets its turn in the event loop. So I hope that makes sense. I just kind of thought of that as I was walking through that example last time. But with that said, let me go ahead and go back to our other examples here. So this example 5, the one that we just saw where we have this time.sleep blocking our event loop, this is exactly what happens when we run any blocking code in our asynchronous functions. So while we're using time.sleep in this example, this could easily be any other code. This could be request.get, making a web request, or any other synchronous code. Because requests, the request library, it's not asynchronous. So to do web requests asynchronously, we would need to use an asynchronous library like HTTPX or AIO HTTP. But if we do have some blocking synchronous code that doesn't have an AsyncIO alternative, then we can also use AsyncIO to pass this off to threads or processes. And the event loop will manage those threads and processes for us. And that's what we're going to see in the next example. So let me open up example 6 here. Now, this example is going to be a bit more advanced here, but I want to show this since it might be something that you'll see or even need to do when working with some asynchronous code. So right off the bat, let me explain a couple of the changes that I made here that are specific to this example since we're using threads and processes. So first, instead of running our synchronous blocking code inside of an asynchronous function, which we don't want to do, I've instead just turned our fetch data function back into a regular non-async function. So it's just a regular synchronous function. And we'll use AsyncIO to pass this regular function to a thread. And then we'll also see an example of how to pass this to a process. Now, you'll notice here that with these print statements, I put flush equal to true argument in there. That's just to make sure that our print statements come out in the order that we expect. Sometimes when running these outside of our current thread, print statements can get buffered and come back in a seemingly weird order. So that's more just for the tutorial here. Now, another thing down here at the bottom where I am starting up our event loop here, you'll notice that I'm also using this if name is equal to main conditional. And this is for our multiprocessing example. So when Python spawns multiple processes, it needs to rerun our script in that new process. So this check makes sure that we don't end up in an infinite loop whenever it runs our code and spawns that new process. Okay, so with that said, let's see how we can do this here. So we still have our asynchronous main function here. And this is going to look very similar to what we were doing before, except when we're creating our task, we're simply wrapping our fetch data function here inside of this AsyncIO.toThread function. This will wrap our synchronous function with a future and make it awaitable. Now you'll notice that I didn't execute the synchronous function. I didn't say, fetch data with parentheses here and pass in that 1. I don't want to do that. You want to pass in the function itself and its arguments separately to this AsyncIO.toThread function so that it can execute later when it's ready. Then we're just awaiting this just like any other task. Now for processes here, this is a little bit more complicated. So first, we have to import this process pool executor up here from concurrent.futures. And then we have to get the running loop because we are using this loop.runInExecutor method here. So here we're just saying loop is equal to AsyncIO.getRunningLoop. And then within this process pool executor, we are creating these tasks with loop.runInExecutor, passing in this process pool executor here. And again, just like before, we're passing in the function that we want to run in a process and the arguments separately. And just like with our threads, that's going to wrap that new process in a future that we can then await. And once we've done that, we're simply awaiting those like we did before. So let me go ahead and run this and see what we get. So we can see that that works and that these ran concurrently. It took 4 seconds, actually a little bit over 4 seconds because threads and processes have a bit of overhead to spin up and tear down. Now the reason it took 4 seconds and not 2 seconds is because we ran these in 2 different groups of 2. We ran both of our tasks in threads, and then we ran both of our tasks in processes there. And since the longest task is 2 seconds, we ran our threads took 2 seconds there running concurrently, and then our processes took 2 seconds running concurrently as well. So just like we've been doing so far, let me pull this up here in the browser and run through this in an animation just to really knock this point home. This code is a little bit longer here, so we can see that some of this gets cut off. But let me go ahead and run through here. I'll scroll down to where we can see that we're starting up this event loop with that main coroutine. Okay, and now we come in here. We are creating this task. We're passing off fetch data with an argument of 1 to a thread, and we're creating a task out of that. So that gets created and scheduled. We're doing the same thing with fetch data and an argument of 2 there. That gets scheduled on our event loop. And now when we await task 1, it's going to suspend our main coroutine here until that task 1 is complete. So now it's going to find our thread here. Now I don't have the code here for our thread. And the reason I'm not showing our synchronous code in this task is because that code isn't running in our current thread anymore. That's going to go off and run in its own thread. So eventually what that's going to do is that task is going to hit and await something that this AsyncIO.toThread puts into place for us. And then it's going to kick off that background thread and run our synchronous code for us. So this thread gets started here running that synchronous fetch data code. It's going to suspend that task. And then we might see some print statements coming in here while that thread is running that synchronous code. But now our event loop is free to move on to our other task here. It's going to run our other bit of synchronous code there in another thread and suspend this second task here. And now both of these threads are going to be running in the background. And then eventually that is going to complete. This thread is going to be done. It's going to notify our 2-thread task here, and that's now going to be ready. Once that is ready, then it's going to return and complete, and then it's going to wake up our main coroutine here since we were awaiting that task 1. It's going to print that that's fully completed. We're going to move on to waiting for that task 2 thread to be done. So again, we've seen all this before. That completes, that's ready. That completes, that's ready. So we're doing a lot of the same stuff here. So I'm going to keep going through this a little bit faster now because should be kind of used to this as we go now. We're awaiting task 1. Task 1 is going to come in here, run. That's going to be a process in the background IO here. It's still printing stuff out here. We're running another process in the background IO. Eventually that's going to complete. That's going to complete there. Our main coroutine is going to pick back up, do some print outs there, wait for that second task to finish there. Once it finishes, it wraps up and completes, and then we move on with printing out all of our code here. Now, I know that that example was a bit more complicated, but I wanted to show that because if we're using AsyncIO, there might be times when we don't have an asynchronous option in order to get concurrency, and we'll need to run some blocking code in threads or processes. But now let's go back to our more standard use cases here. So this is our last example here before I get on to a real world example, and we can see how to update a real code base to asynchronous. So with example 7 here, in this example, we're going to see other ways that we can schedule and await tasks. So far, we've been creating tasks and one at a time and awaiting them manually. But a lot of times, we might want to create a bunch of tasks and run them all at once. We can do this with either gather or with task groups. So here, our first section here, I've just taken out some print statements along the way, but our first section here is basically what we've been doing. We're creating these tasks manually, they get scheduled, then we await them manually and get those results. Now our next example here, what we're doing is we are creating and awaiting a bunch of coroutine objects in a list, and then we are awaiting those with AsyncIO.gather. So what I have here is just a list comprehension. We're saying that we want fetch data for I in range of 1 to 3. So that's still only going to give us 2 there, fetch data 1 and fetch data 2. And then we are passing those in to AsyncIO.gather, and then we are awaiting that gather. And I'm going to go over these in more detail in just a second, but let's move on to look at this task group here as well. Oh, I'm sorry, this isn't the task group. This is another gather here. In this one, instead of creating a list of coroutines like we did up here, in this one, we are creating a list of tasks, and those tasks are just wrapping those coroutines there. We can gather those as well. So here I have a list of coroutines that I'm passing in to gather. Here I have a list of tasks from those coroutines that I'm passing in to gather. Down here with the task group, here, I'm just saying task group as TG, and then within the task group, we're doing a list comprehension here of tg.createTask on that coroutine there, and we're getting those results. Now we're going to look at all these more in depth here in just a second, but let me go ahead and run these and we can see the output here before we go over this code a little further. Okay, so this took 8 seconds total. Now these did all run concurrently. We ran these in 4 different groups, and each group took 2 seconds. So that's why it took 8 seconds total, 2 seconds for 4 groups. Now, we've already seen our manual task creation up here plenty of times so far. So let's skip over that and let's go to our AsyncIO.gather here. Now, when it comes to gather, you'll notice that these asterisks that I'm using here before our list. Now, what this is doing is it's unpacking our list. Now, gather doesn't take a list as an argument, so unpacking it with this asterisk is basically the same as passing all of these items from this list in individually. Now, for these 2 gather examples here, one of them I'm passing in coroutines directly, and the other one I'm passing in tasks. Now, you can pass in coroutines directly if you just want to get the results, but remember that tasks add some extra functionality. So if you want to monitor or interact with the tasks in any way before they complete, then you'd want to use tasks. But if you just want the results, then it's fine to just pass in that list of coroutines. Now, for our task group here, this is the first time that we've seen an async context manager. Now, just like functions, context managers can be async when they need to do I/O operations during setup or teardown. That's why we have async with here. So task group does a lot of async work for us when entering and when exiting. So it tracks tasks, it waits for completions, handles cancellations, handles errors, stuff like that. Now, the main thing that you'll notice is that we're not awaiting anything with the task group. We're not awaiting these results anywhere, and we're not awaiting them once we get out of that context manager either. It awaits all the tasks that we create for that task group for us when it exits this context manager. And we'll see another example of an async context manager here in a bit that isn't a task group. They can be used for things that need to set up and tear down, for network requests, file access, database operations, all kinds of stuff. Now, you might be wondering which ones you use here. Should you use gather for a bunch of different tasks, or should you use a task group? Now, I tend to use task groups a lot of the time, but basically the key difference between gather and task groups is how they handle errors. So with AsyncIO.gather, if you use the default of return exceptions is equal to false, which I honestly wouldn't really recommend. And as a matter of fact, I didn't realize that I didn't have return exceptions equal to true here in gather. So I would always recommend, if you're going to use gather, to use this return exceptions equal to true. The default is false. But with that set to false, if one task fails, then it raises the first exception that it saw. You don't get a bundle of errors or any of the successful tasks. And if it fails, other tasks won't be canceled. So you risk having orphaned task. Task group, it also fails quickly, but it gives better errors and handles cleanups a bit better. So I wouldn't really use gather with its default argument of return exceptions equal to false, but it does have a good use case for return exceptions equal to true, because if any task does fail with return exceptions equal to true, it still runs the other task for you. Every awaitable in that gather finishes, whether it succeeds or fails. So then your result is just a list where each position is either the result or of the success or the exception of the failures. This is what you want to use if you want to run all the tasks, even if some error out. Like maybe you have a bunch of URLs that you want to crawl, but you don't want all of them to fail if only one of those URLs fails and gets hung up or doesn't exist or something like that. For that, you would use AsyncIO.gather. Now with AsyncIO.taskGroup here, it also, on the first failure, it cancels all the other tasks. So if it fails, it raises an exception group containing all exceptions from the failed tasks. And that would include exceptions from canceled tasks as well. Now, there's no option to keep running other tasks after one fails. So we use this when we want all our tasks to run successfully. So basically, to sum all that up, if you want tasks to continue running, even if some fail, then you would use gather with return exceptions equal to true. Now, but if you want all of the tasks to either fail together or succeed together, then you would use a task group. And I almost never would recommend using gather with the default of return exceptions equal to false. If somebody knows of some edge cases that I'm not thinking of, then feel free to leave me a comment. But, if that's the case, I would, if you want it to fail fast, then I almost always use a task group instead. Okay, so just like with the other examples, let's look at this example in the browser here to see what's going on under the hood. But I'm going to run through this animation a little faster because it's going to be very similar to the examples that we've already seen. The tasks are going to be scheduled and awaited in different ways than we've seen before, but the behaviors are basically the same. So let's step through this pretty quickly here. We're creating a task, it gets scheduled, creating another task that gets scheduled. We are awaiting our main coroutine here and suspending it, running our first task, that suspends. Our second task suspends after we kick off both of these background IO tasks here. And actually, so I'm not scrolling here, let me make the screen a little bit smaller. I know that's going to be harder to read, but basically we just want to see these animations anyway. The code is the same as it was in our example here. But this is the examples that we've seen already where we're creating these manually. That's why I'm stepping through these pretty quickly. Okay, so now we are getting to our gather examples. So first, we're creating this list of coroutines here, and that's not going to schedule anything on our event loop. And now we are here where we are gathering all of those, and we are awaiting that gather. Now, since these are coroutines, these are going to get scheduled and run to completion at the same time. So that is going to suspend our main coroutine and schedule all of those coroutines that were in this list. So now, just like we saw before, whoops, let me get that there. Just like before, it's going to run through. Since we have both of these scheduled on our event loop, it's going to run these concurrently until these complete and return, and complete and return. And once all of those are done, then it's going to tell our main coroutine here that it's ready, and it's going to go ahead and move forward. Now with our gather task, this is a little bit different because we are creating tasks here in a list instead of creating coroutines in a list. Now remember, when we create a task, it's going to go ahead and schedule those. So those get scheduled when we create those tasks, and then when we await those, that is whenever we are going to suspend our main coroutine, and our event loop can actually get around to running those. But those are going to run concurrently like we've seen before. And once those are done, then our await is going to go ahead and wake up our main coroutine here and go ahead and move forward. And then with our task group, we're going to come in here to our task group. We are going to create these tasks in our task group. So those are going to get scheduled onto our event loop. Now there is no await statement here. This automatically awaits whenever it exits our context manager here. So once that context manager ends, that's when we suspend our coroutine there, and then our event loop can find these ready tasks and run these. So just like before, these are run concurrently, and once those are done, that's whenever it can fully exit that task group context manager there and move on to our print statement that it has those task group results. So then we are finished up with our main coroutine here. That completes. Down here at the bottom, we are free to move on and print out our results. Okay, so that is the last animation, and that is the last of our code examples. Now we can look at a real world example here. I hope that those animations really helped visualize what's going on in the background and helped make it easier to understand how AsyncIO works. With my brain, I can kind of understand stuff better when it's visual like that and interactive like that. But now let's look at a real world example, and we'll see how to convert this real world example of some synchronous code and convert this over to using AsyncIO. So let me open up this real world example here, and first we'll just look over what this does. So I have a synchronous script here that downloads some images, and then it processes those images. So let me walk through this and explain what's going on. So I have my imports up here. I have my image URLs. This is just 12 high definition pictures here. And then I have a download single image function, download images function that loops over those URLs and downloads the single images for each of those URLs. We have a process single image here, and I just grabbed this offline. This is an algorithm that does edge detection on photos, so it's just some photo processing there. We have a process images here that loops over all of the images that we need to process that we downloaded and processes one at a time. And then we have our main method here. And in our main method, just ignore, I have a bunch of timing stuff here. just to see how long this script takes to run. But the big part is that we have our image paths where we are downloading all of our images, and then we have our process paths where we are processing all of those images that we downloaded. And then I have some final wrapping up here with the timing, and then I'm printing out all the images that we download and how long everything took. And then finally down here at the bottom, I am running that main function. So let me go ahead and run this, and we'll see how long this synchronous script takes. So we can see that we are downloading some images here, and I might fast forward a little bit until this is done. Okay, so I fast forwarded a bit there just so we didn't have to watch all of these images download and process. But at the bottom, we can see how long this took. I'm actually going to copy this so that we can reference this later. I'm going to paste it into some of my notes here off screen. But we can see that the total execution time here was about 23 seconds. The time that it took to download the images was 13 seconds, which was 55% of the total time, when we processed our images in about 10 to 11 seconds, which was about 44% of the time. So we're going to be able to speed this up by a lot. But I don't know about you, but when I was first learning AsyncIO, I didn't even really know where to start with, in terms of where to make changes to the synchronous script. Which parts do I make asynchronous? Do I use threads or do I use processes? How do I know? Well, here are some tips that I can give to give you an idea of where to start. So first, we need to determine what's IO bound and what's CPU bound. Like I said before, IO bound work is where we're just waiting around on external things to be done, like web requests, database access, file access, things like that. It's often easy to guess what's IO bound in your code if you know what you're looking for. You can even look for certain words, words like fetch or get or web requests or database. Those usually lean towards IO bound type of things. Certain words like compute or calculate or process, those usually lean towards CPU bound type of tasks. Now, once you work with this stuff more and more, that's going to become more intuitive. But if you want to be absolutely sure, we can use actual profiling tools to see where we're spending the most of our time in our code. So I'm going to show a profiling example using Scaling, which is a really nice profiler that I like. And we're not even going to need to add anything extra to our code. So first, I'm going to install Scaling here, and you can install it with pip or UV. I'm going to use UV here. So you could do a pip install Scaling. I'm going to use UV and do a UV add Scaling. I think I spelled that right. And once that's installed, I'm going to run a command that will profile our code. Now, I have some snippets open here that I'm going to use to copy this command in just so I don't mistype anything here. So let me copy this and then paste this in. Now, since I'm using UV here, I'm doing a UV run -m. You can also use a Python -m there. So I'm running this scaling module. I'm creating an HTML report here called profile report, and we are going to profile, my script here is called real world example sync v1. So I'm going to run that, and it's going to rerun our script where it's going to download those images and process those images again, but it's going to profile it as it goes and give us an idea of where we're spending most of that time. And once this is done, I will go ahead and open this profile report.html in my browser. Okay, so that script finished. It actually took a good bit longer that time. That time it took 29 seconds. The last time it only took 23 to 24 seconds. But let me go ahead and open this profile report that it gave us here in the browser. I will allow that. Okay, so here's our report. Let me make this a lot larger here so that we can, so that you can read this. Okay, so we can see here that it breaks up the time here between Python time, native time, and system time. Now, the system time is likely a lot of waiting on I/O here. And we can see that most of our system time is here in this download single image function here. So that is a great indicator that we can speed up this download single image with AsyncIO or threads, if you want to use threads also. Now, a lot of the time being spent in Python is here within our process single image function. So that likely means that that is CPU bound. So we'd get more of a speed up using multiple processes on that than we would from AsyncIO or threads. So now that we've profiled this, we have some actionable knowledge of where we can speed up our code. So let's go change these specific functions. So I'm going to go back to our Python code here. I'm going to close down our output there. And now let's go to the top and let's import AsyncIO. Now, for this first example, let's assume that I don't know about any asynchronous libraries that we can use to do these web requests. So there are asynchronous libraries out there that make this easier, like HTTPX or AIO HTTP. But let's say that for now, I just wanted to keep using requests. We can see here that I'm using a request session here, and I'm using a session.get with that request library. Now, like I've been saying, request isn't asynchronous. So to continue using requests, we really don't have any choice other than to use threads. We saw how to do this earlier. So let's go ahead and change this to use threads and have AsyncIO manage those threads. So I'm going to go up to our download single image here. Now, the first thing I'm going to do, I don't know if these sessions are thread safe. So I'm going to remove this session as an argument here. And I'm just going to use request.get instead of session.get there. That'll have to create a new session every time for each of those URLs, but that's okay. But other than that one small little change, since we're going to use threads for now, I'm not going to touch this function anymore. I'm going to leave this as a regular synchronous function. I'm going to go to where it's calling this function to make the changes that we need. And it's calling this function in our download images function here. So within download images, this is where we'll use AsyncIO to send this off to threads. So that means that we're going to convert this to a coroutine. And to do that, the first thing that we need to do is add async before the function here. And I'm no longer using sessions since I wasn't sure if that was thread safe. So I'm going to take out that context manager there and unindent those. And I'm no longer passing in that session as an argument there. Okay, so now we're running this single download single image function for every URL in our URLs list. So instead, let's send that off to a thread. To do this, we can use gather or we can use a task group. I'm going to use a task group. And I'm actually going to grab a little bit of code from my snippets file here, and I'll paste this in above what we have now so that we can see the difference. I just don't want to accidentally mistype anything and have to do a bunch of debugging in the middle of a tutorial. So let me just copy this from my snippets here. And so this is what we had before, and this is what we have now with this task group. So you can see here that we are creating our task group here, and within here we're creating a bunch of tasks, and we're saying task group.create task. And now instead of running this download single image directly, we're now sending this off to an using AsyncIO.toThread. And this create task method here is going to create tasks for us of all those threads that we can await. Now, like we saw before, this task group is going to await on its own after it exits this context manager here. So outside of this context manager, to get the results from all of those tasks, I can just create a new list here and say task.result for task in tasks. So now that we have that, I'm going to go ahead and just remove what we had before and use this new way of doing it here and save that. And now, just to show that it's important to know when to use AsyncIO versus threads versus processes correctly, let me also shove our image processing off into threads also. Judging from our profiling that we saw earlier, our processing should be CPU bound, so we shouldn't get any speed up by shoving these onto threads, and I want to be able to show that. So let me go ahead and put those in threads just so we can show that we don't get a speed up there. So I'm going to go down to our process images function here, and I'm also going to make this a coroutine as well. And just like we did for our downloads, let me go ahead and grab a small snippet here. This is going to be very similar to our downloads code here. Again, I'll put it right above what we had before, but we are basically doing the same thing here. We're creating a task group. Within that task group, we're creating a bunch of tasks, and what those tasks are is we are passing this process single image here off to a thread. And it's going to do that for every image that we have in our list of images. And then once we exit that context manager, we are just getting another list comprehension here, setting the task.result for every task in that task list. Okay, so now I'm going to remove the old way of doing that there. Now, I can't run this quite yet. Since we converted these to coroutines, we now need to await these and also run an event loop. So we're calling these process images and this download images here. We are calling those within our main function here. So within our main function, I'm also going to convert this to an async function because I can't await those if I'm not in an async function. And now that we are in an async function here, instead of setting our image paths equal to download images, I'm instead going to await download images, since that's now a coroutine, and I'm also going to await process images as well. And lastly, where we are running our main function down here, this is our main function is now the main entry point for our asynchronous code. So we need to run that in an event loop. So to do that, I'm going to say AsyncIO.run, and I'm going to pass that in to run. Okay, so hopefully I typed everything correctly there. Now let me rerun this and let's see if we're able to get a speed up by passing all of those off to threads. So we can see that it kicked off a lot of downloads really quickly and downloaded those, but the processed images, it's still taking a while here. And you can see with threads, some of this output gets buffered a little weird and puts them on the same lines, but that's okay. We're not too concerned about this weird output up here. That's just showing us what those threads were printing out with the process images and stuff. This is mainly what we're concerned with here, is how long it took. So right off the bat, you can see that it sped up these downloads by a lot. They all ran in their own threads concurrently. Before, I wrote this down here, before our download of 12 images took 13 seconds, and now it's taking 2 seconds. And our process images last time took 10.49 seconds. Now it took 10.63. So it sped up our downloads by a lot, but it didn't speed up our processing, which we expected. So that's good. So it's showing us that we sped up our IO bound code, but not our CPU bound code. Okay, so now let's take another look at how we can improve this code. So right now, we've just shoved everything off to threads, but you really only want to do that when there's no asynchronous alternative. But for web requests, we do have AsyncIO compatible libraries. The two most popular are HTTPX and AIO HTTP. I'm going to use HTTPX in this example because it's more similar to requests. And we've also got some file reading and writing that we can pass off to an asynchronous library as well. And for that, we can use AIO files package. So let me go ahead and install these. I'll open up our terminal again here. Now, just like before, you can use pip install, or I'm using UV. So I'm going to add these with UV. So I'm going to use HTTPX for the web requests, and I'm going to use AIO IO files for the file IO. So now that we have those installed, let's go up here and let's update our imports. So I'm going to import HTTPX. I'm also going to import AIO files, and I'm no longer going to use requests, so I'm going to get rid of requests there. And also for our image processing, we saw that the threads didn't speed that up, which we knew was going to happen. But I wanted to show how someone might try that anyway. But instead, let's pass those off to processes. So adding additional processes for that work is how we speed up CPU-bound tasks. So to do this, I'm going to import the process pool executor from concurrent.futures. So that's from concurrent.futures, and we are going to import the process pool executor. Okay, it automatically sorts my imports there, so if those jump around, don't worry about that. Okay, so now let's turn our download single image function here into an asynchronous function that uses HTTPX. But first, I'm going to update the download images function here first. And again, I'm going to grab this from my snippets file, and I'll explain what we changed just so I don't mistype anything here. Let me grab this from my snippets and paste this in, and then I'll explain what we changed here. Now, if you remember, before I passed this off to threads with the request library, I was doing something like this with requests. I was using a request session, which basically allowed me to reuse the same session for every download. It's going to be the same thing here with HTTPX and this async client. I'm going to reuse this same client for every download. So we are using this. This is a context manager here. So we are opening this up, and we have this asynchronous compatible client here. And then I'm creating my task group. And then we are creating a bunch of these tasks. We're no longer sending it off to a thread. Now we're just passing this in directly. And now we're also accepting this client here, which I took out of the threading example. So let me go back up here and add this back in. So that was client, and that is going to be an HTTPX dot async client there. And now, instead of doing request.get, that's going to be a client.get. Okay, so now we are making this download single image function here asynchronous. So we're going to make that asynchronous there. And let me clean this up a little bit here. Okay, and now again, I'm going to grab some code from my snippets file here. Now I know I'm doing a lot of copying and pasting here, but this tutorial is getting pretty long already as it is. So I'm trying to use time here as effectively as I can. So this was I'm just copying and pasting some code here because while this is very similar to requests, it's not exactly like requests. So I want to paste this in, and I'll explain the differences here. Okay, so the first big difference before, where we were doing this response equals, this was request.get here. Now, instead of that, what we are doing is we're doing an await on this client.get here with that async client. And also one other small change is that with the request library, it's allow redirects. This one is follow redirects. And also down here at the bottom, we were using normal file writes, but now we're using these AIO files to write asynchronously. And also, I believe that this is the first time in this tutorial that we've seen an asynchronous iterator here, where we're looping over these chunks from our response. Now, normally with a regular iterator, the for keyword here just pulls the next value immediately. But here, every next chunk may involve waiting for I/O, like network data arriving. So Python gives us this async for to handle that gracefully. And this response.aItterBytes here gives us an asynchronous iterator. Under the hood, each loop step does an await to get the next chunk. That's why you have to write async for chunk in blah, 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 blah. And inside that loop, instead of using f.write, we are awaiting that f.write, because now that chunk and this file here, everything here is asynchronous. Okay, so let me go to where we're processing our images, and I'll convert that to using processes instead of threads. So down here is where we were sending this off to threads. Now, if you remember from our examples earlier, using processes is a little more complicated. Let me grab that snippet here so we can see what this looks like. This is the last snippet that I have in my file here, so it's the last one that I'm going to be grabbing. So let me paste this in here. So we saw this in one of our earlier examples, but we have to get the running loop using this AsyncIO.getRunningLoop. Then we are using this process pull executor here. We're creating a bunch of different tasks. We're doing loop.runExecutor with this process pull executor, passing in that process single image with the argument. And we're doing that for all of the paths in our list of paths there to process. And then we are awaiting those with AsyncIO.gather and passing in all those tasks there. Oh, and since I explicitly gave that hint earlier, I'm also going to do the return exceptions equal to true and follow my own advice there and do that. Okay, so now we're passing this image processing off to processes instead of threads, and our download images are running asynchronously on our current thread using AsyncIO compatible libraries. Nothing else should need to change in our main function. So let's go ahead and run this and see what our speed up is now. This should go much, much faster here. Okay, so that was obviously much faster. You can see here that we ran this basically in 4.9 to 5 seconds in total. Compared to earlier, I wrote that down. Our total execution time was 23.54 seconds. Our downloads are now down to 1.6 seconds. Before, that took 13 seconds, and our processing only took 3.25 seconds when before that took 10.5 seconds. So a big speed up on everything there. Now, like I said, I know that this video is getting long, but one more thing before we end here, I want to show you some very quick things that we can add in here that you'll likely use at some point in your actual code. Now, it's nice that we've sped this up so drastically, but we're being a little greedy here in our script. So right now, we're only grabbing 12 URLs, so it's not a huge deal to run all of these concurrently at once. But you might get into a situation where you're downloading thousands of URLs or trying to do thousands of things concurrently at the same time. If that's the case, then you might want to add some limits in place so that you're not kicking off all that stuff at the same time. It can bog down our own machine, and it can also hammer servers. So one easy way that we can do this is to use something called a semaphore. And for our processes, we can easily get our CPU count of our current machine to limit the number of processes that can be spun up at a time. So let me add both these to our code. First, let me go up here. Let me go up to the top here. I'm just going to import OS here so that we can get our CPU count. And now at the very top of our code, I'm going to add in a couple of constants here. I'm just going to call one of these download limit, and I'll set this equal to 4, so we can do 4 concurrent downloads at the same time. I'll create another one here called CPU workers, and I'll set this equal to os.CPU count. Now, to use a semaphore, I'm going to go update our download images function here. Right before we open up our async client, I'm just going to say that our download semaphore is equal to an AsyncIO.semaphore, and we're just going to set that equal to that download limit, and our download limit was a constant of 4. Oh, and just so I don't screw up later, let me fix that typo. That is a semaphore there. And now I'm going to pass this in as an argument to our download single image function here. So I'll just pass this in as the last argument there. It's giving me an error because we're not accepting that right now. Let me go up here and accept that. I'll just call this a semaphore, and then to type in that, I'll say that that is an AsyncIO semaphore. Okay, clean that up. And now to limit this to 4 downloads, I'm just going to take everything in this function here, and I'm going to say async with that semaphore argument there. And I am just going to put everything here inside of that. And that's going to use that semaphore, which will limit the maximum concurrent downloads to 4 at a time. Now, for our processes, this one is actually the easiest part for once. So all I have to do is pass in our maximum number of workers here to this process pool executor. So I'll say max workers, and I'll set that equal to the CPU workers constant that we set there at the top, which was equal to the CPU count on our machine. So with those changes, we're not being so greedy anymore. So even if we had thousands of images to download and process, we're still doing them quickly, but not trying to spin up everything all at once. So now if I save this and run it, whoops, I have a mistake here. Let me go see what I spelled incorrectly here. Oh, you guys probably saw that. I need an equal sign there instead of a minus sign. I hit a typo there. Okay, so now let me rerun this again. And now we can see whenever we first kicked that off, all 4 of these started at once, and then it waited for one of these to come back before it started another one. So we have 4 concurrent downloads going on at a time, but that is the max, is we're not sending off more requests until one of those 4 are done. So overall, our speed is going to be slightly slower than before, but you're definitely going to want to use these limits like this once you get into doing a lot of work at once, just to be easy on your machine and also to be easy on other servers. We still have a huge speed up here, not as much as a speed up as just blasting everything off all at once, but we're using some smart limitations here and also getting a big speed up. So it's the best of both worlds. Okay, so we're just about finished up here. We covered a lot in this video, so let's start to wrap things up a bit. So first, I'd like to reiterate some common pitfalls that you'll run into when you first start working with AsyncIO. One mistake that many people make that you can see from time to time is forgetting to await their tasks or their coroutines. Just to show a very quick example of this, let me go back to one of these examples here. And so for example, let's say that we don't await these tasks. Okay, whoops, let me delete that. Let me run this code here really quick. Now we can see that we got some print statements and stuff like that, but we're not getting any actual errors. But if you look closer, then you'll notice that these tasks didn't actually run. You can see that they are printing out when we got the results to these that these tasks were canceled. But if we didn't have a return statement here and I was to run this, now we have a bunch of print statements with no errors at all. And it looks like things were kind of successful. But if we look closer, we'll see that these tasks never actually ran and it just got to the start of those and they never finished. So let me undo the changes that we made to that. Now, another issue that you might run into that's pretty common is that a script can end before tasks are complete, which you likely don't want. So here, where we are awaiting our task 2, let me change this, and instead of awaiting task 2, I'll just await an AsyncIO.sleep, and I'll just do this for 0.1 seconds. Now, that task 2 normally takes 2 seconds to complete. If I run this here, then we can see that we didn't get any errors here, but we got done with our first task, but we never got done with our second task. It says that task 2 was fully complete. That's just because I still have this print statement here. But what we were awaiting was this AsyncIO.sleep. If we actually look at our results here, we can see that we have a result of 1, but we do not have a result of 2 there. So you want to make sure that all of your tasks are awaited and that you don't have any still running before your script is completely done. Now, of course, another one of the most common mistakes is accidentally using blocking I/O calls within async code. We saw this several times throughout the video. So how do we avoid some of these issues? Well, one thing that helps is a good linter. My rough linter settings point out a lot of AsyncIO mistakes for me. If you haven't watched my video on rough and want to see how I have mine set up, then I'll leave a link to that video in the description section below. And also, if you set debug equal to true here, debug is equal to true with this asyncIO.run, then that will help you find a lot of things that might be wrong in your async code as well. But you just want to make sure that you have that debug set to true only whenever you are working in development. And lastly, just to reiterate when to use AsyncIO versus threads versus processes, you'll usually want to use AsyncIO when you have some IO-bound work that you want to run concurrently. As long as there are asynchronous libraries to do that in AsyncIO, then I would recommend doing it that way. If there aren't asynchronous libraries available and you have to use synchronous code for your IO-bound work, that's when you'd want to use threads. And multiprocessing is what you'd reach for in order to speed up CPU-bound work. And if you're unsure of what is what, then you can reach for a profiler like we did earlier to see what's going on under the hood and where your code is spending much of its time and what that time consists of. So there's more and more AsyncIO compatible libraries popping up all the time. And the more libraries that are built on top of it, the more it'll allow us to use it in our own code. We have web frameworks like Fast API, HTTP clients like HTTPX and AIO HTTP. There are database drivers. SQL Alchemy supports asynchronous now, and there are asynchronous drivers for Postgres, MySQL, and others. There's also the AIO files for file IO and many more out there. So it's definitely a growing ecosystem. But with that said, I think that's going to do it for this video. Hopefully now you have a good idea of how to use AsyncIO in Python. Even if we didn't get into a specific example of what you were hoping to see, like maybe asynchronously connecting to a specific database that you use or something like that, I hope that you now feel like you at least have more of a grasp on how this works under the hood and also have a mental checklist of how you'd prepare using AsyncIO and some ideas for how to use this in your own projects. I'm going to be putting all of the code and animations from this video on GitHub, and I'll also add the animations to my website, and I'll put links to those pages in the description section below. In a future video, I'm going to be showing how to use Fast API, which is a really fast web framework that leverages AsyncIO and lets you use the async await patterns that we've learned here to build web APIs that can handle many requests concurrently. So hopefully this tutorial will allow you to fully understand what's going on there when we see that in action. But if anyone has any questions about what we covered in this video, then feel free to ask in the comment section below and I'll do my best to answer those. And if you enjoy these tutorials and would like to support them, then there are several ways you can do that. The easiest way is to simply like the video and give it a thumbs up. Also, it's a huge help to share these videos with anyone who you think would find them useful. And if you have the means, you can contribute through Patreon or YouTube, and there are links to those pages in the description section below. Be sure to subscribe for future videos, and thank you all for watching.